Hey guys, so we were discussing applications of derivatives. In other words, why do we need derivatives, right? So what are the benefits of derivatives? So today we want to discuss how we can use sort of derivatives to determine whether the function is increasing and decreasing, and how this also helps us in considering local extrema. So let's get started. Our objectives are we discuss increasing functions and decreasing functions, and then we will discuss first derivative test for local extrema. So increasing functions and decreasing functions. So let's get started with definition. A function is, we say, increases over an interval if the graph rises from left to right, right? When we move from left to right, it has to rise. And we say it decreases if the graph falls, right? Again, if you move from left to right, it has to fall, right? So an example of an increasing function is, say, from AB, something like this, right? So it always increasing, right? Increases. And an example of a decreasing function from A to B, so it starts falling, right, as I move along AB. Okay, so this is decreasing. And we say that the function is monotonic if it's increasing or decreasing, right? If one of them is the case in an interval, then we say it's a monotonic function. Sometimes we also call monotone increasing or monotone decreasing. So the question is, how can we use of a derivative to find out whether the function is increasing or decreasing? Okay, so here is the theorem, or corollary 3 if you like. This is the corollary 3 for the mean value theorem, right? So this is another consequence of mean value theorem, the theorem we saw in the previous lecture. So what it says is the following. So my function, let's say, is continuous on AB and differentiable on open interval AB. If you happen to know that the derivative is positive at every point AB, then f is increasing. And if the derivative is negative at every point on AB, then it's going to be decreasing. Okay? So why is that? And how can we use the mean value theorem? So if you forgot the mean value theorem, refer to the previous video lecture. Well, again, increasing means I want to show that for any x1, if I move from x1 to x2, I want to show that it's increasing, so it has to rise. So f of x1 must be smaller than or equal to f of x2, right? In fact, it's streak, so it's going to be streak also here. So I want to show it's streak. Well, so this is a question, right? By MVT, what do we know? We know that there is a C such in x1, x2, such that f prime of C is equal to f of x2 minus f of x1 divided by x2 minus x1. Okay? Now, in the first occasion, right? So let's assume that all the derivatives are positive. Well, this means, in particular, this derivative is also positive, right? Well, what is x2 minus x1? So this bottom, right, the denominator is positive. So, and then the numerator must be positive, right? Because the only way you can get positive is if you divide a positive by a positive, because we already know denominator positive, right? So this implies that my f of x2 must be bigger than f of x1, right? So this implies this is increasing, right? If I were, if in the second occasion, if f prime was negative, then we would get the opposite inequality, in which case we would get the decreasing function, right? So that's a very simple application of mean value theorem. Very nice. So now we can use the derivatives to find out where my function is increasing and where it's decreasing and so on and so forth, right? And this is a very useful information to better understand the function. In particular, if you would like to sketch the graph of the function, I think this information will be very important. So let's do an example. So let's say that I'm given a function x cubed minus 12x minus 5. So here's the graph given on the right. I would like to identify the open intervals on which the function is increasing and open intervals on which the function is decreasing, right? Well, if you look at the graph, I mean, so we want to do this without looking at the graph, right? But if you look at the graph, we see that at this point, so in here, right, this is like minus infinity here, the function is decreasing, right? Oh, sorry, increasing, right? If you move from left to right, it's increasing. And from this point to here, we see that here it's decreasing, right? And then from 2 onwards, right? From 2 onwards, we see that this is sort of increasing, right? So graphically, that's what we see it. Now let's find out whether we can arrive at the same conclusion just investigating the function. Okay, so what was the case? So if the function has a derivative positive, then it means there it's sort of increasing. If the derivative negative, then it's decreasing. So we have to analyze the derivative, right? So let's take the derivative. What is this? This is 3x squared minus 12, which is 3x squared minus 4, which is 3x minus 2 and x plus 2, right? So I want to find out whether when this function is positive, when this function is negative, right? So for this, I need to find the roots of the function, right? Where it's 0, it's not negative, not positive, so 0. Because there we will see the change of sign, right? So we see that if you set this equal to 0, so if you like, I'm sort of finding the critical points of my function f. Then we see that x equal to 2 is an important point, and x equal to minus 2 is another important point. So now what I do is I will go ahead and sketch the real line and plot my two values. Here's my 2 and here is plus 2. Right, now what do I do? So basically it suggests that I have one type of behavior, here I have another type of behavior, and here I have yet another type of behavior. So I need to decide. So what do I know about when x is less than minus 2? So for example, you can pick here, right? For example, I can pick minus 3 here, right? So if you let x equal to minus 3, if you substitute, what is your derivative? This is going to be 3 minus 3 minus 2 minus 3 plus 2. So this is positive, negative, negative. So this is going to be positive, right? This is positive. So we see that here my function is positive. Here it's positive, right? Now, how about on an interval from minus 2 to 2? From minus 2 to 2, I can pick again any point. Okay, you can pick any point. For example, I can pick 0. Right? So if you let x equal to 0, then what is your f prime of 0? Well, this is 3 times minus 2, and x plus 2 is just 2. So this is negative, right? So here I see that my function is negative. So you don't have to check every single point, just you check one point, because we already determined 2 important points where we might have some changes, right? Some changes in the sign. And finally, I need to pick one point from 2 to infinity. So you can pick any point. I don't know. For example, let's pick 4, right? I can pick 4. And then if you let x equal to 4, f prime of 4 is going to be 3 times 2 times 6. So this is all positive, right? So we see that here it is positive. This is positive. Yeah, sorry, this is negative. So I confused myself. Here this is negative. So what it says is, long story short, here my function is sort of increasing, here my function is decreasing, and here my function is increasing. Okay, so indeed that's what we see, right? Here my function is increasing, here it's decreasing, here it's increasing. Great. Here's an important application. So this is called first derivative test for local extrema. If you remember in 4.1, we discussed how to find global extrema, right? How do we find maximum and minimum? Now we want to find out not only maximum minimum, but we also want to investigate all the local maxima and local minima, right? So we already know that local maximum or local minima occurs at a point where the derivative is 0 or where the derivative doesn't exist, right? At the critical points. However, let's say that we found one point. So let's say that I found this C1 where the derivative is 0, right? Okay, how am I going to decide whether this is local extrema, whether it's minimum or maximum, or it may be neither, right? Like in this case. Well, here, for example, at C2, we know that this is local maxima, right? Because at these nearby points, my function is lower, so this is sort of the peak. So that's why this is a local maximum, right? Let's look at the behavior. If I sort of get closer to C1 from left, what's happening? My function is increasing, right? What does that mean? It means the derivative here is positive on the left, right? But then when you pass C2, if you go keep increasing from C2 onwards, then we see the function must be sort of decreasing in the nearby, right? So decreasing means the function has a negative derivative, right? So what can we say? So how can we sort of make it into a theorem? Well, you find the critical point, and if on the left it's negative, sorry, positive, and on the right it's negative, then it's local maxima, right? So where it is, so here's the first derivative test. Suppose C is a critical point, right? So that f is differentiable at every point in some interval containing C except possible at C itself, moving across this interval from left to right. So what I told you is the two. If f prime changes from positive to negative, right? So here it was positive, then it became negative, right? The f prime, not f itself, the f prime, the derivative. Then this f is going to be my local maximum. Now let's look at the local minima right here, right? C3. So what's happening? If I'm approaching C3 from left, this is decreasing, right? So the derivative is going to be negative. But then once I pass C3, my derivative becomes positive, right? Because this is increasing, right? So so this is the one. So if f prime changes from negative to positive, right? From negative to positive, then this point C3 is local minimum. Okay? So if f prime doesn't change sign, etc., then we cannot. There is no extrema. Like in here, right? Here my function is positive. I mean, it's increasing, and it's still keep increasing, right? It's still keep increasing. Here it becomes sort of horizontal, but it keep increasing. So this is not a local maxima and not a local minima, right? It's obvious from the graph. Okay, so that's the content of the third part of this theorem. All right, an example. Given a function f of x, I would like to identify the intervals where the function is increasing, where it decreases, and moreover, I would like to investigate local and absolute extrema values, right? So for all this, I need to uh, look at the derivative, right? So I need to find the critical points. So let's go ahead. Let's take the derivative. What is the derivative of x to the 4 over 3? Well, this is 4 over 3x to the, if you subtract 1, this becomes 1 over 3. And then if you take the derivative of x to the 1/3, this is going to be 4 over 3 x to the, you subtract 1, so it becomes minus 2 over 3, right? So I can take out 4 over 3. Here I get x 1 over 3 minus here I can write it as x 1 over x to the 2 over 3. So I can bring to the common denominator, which is x to the 2 over 3. Then I need to multiply x1 over 3 by x2 over 3, which becomes just x minus 1, right? So now I set this equal to 0, right? So I set this equal to 0 to investigate the critical points. What is the critical point? Well, so critical points are, so x equal to 1, right? Then it's 0. But remember, critical point also means the points where the derivative does not exist. And we know that if x is 0, then the derivative doesn't exist, right? So these are two points. I haven't given any interval, so I'm regarding it as from minus infinite to infinite. Great. So let's plot this point 0 and 1, and let's see where my function is positive, negative. So if my function is sort of less than 0, what happens? What happens if x is less than 0? If x is less than 0, my x minus 1 becomes less than 0, but this is like x to the 2 over 3 means like x, it's the cube root of x squared. So the denominator is always positive. So the sign is determined by x minus 1, right? So here it's negative. How about between 0 and 1? Between 0 and 1, again, if x is less than 1, it's again negative, right? So here it's again negative. And here, when x is bigger than 1, this is positive, right? So my function is decreasing here, decreasing on this interval, and then here increasing. In fact, that's what we see, right? So it looks like this is my point 1. So here my function is decreasing, 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 and starting from 1, it started increasing, right? Okay, now, how do we investigate absolute extrema and local extrema? Well, first of all, what we can do is let's investigate the local, right? Local. So what we see here, my function is decreases and then increases, right? And at 1, I know it's 0, right? It's critical point. So what I can see here is, here I have local. So at x equal to 1, I have local minima, right? But at 0, we don't have anything, right? Because it decreases and then it's keep decreasing, right? Here it decreases and it keeps decreasing. So there is no local maxima and no local minima. But then what is the shape of the function? So the shape of function, so it sort of decreases and then increases, right? So as you can see, sort of we don't have any restriction here. So what we see is the function is sort of coming from plus infinite and going back to plus infinite, right? You can also see it if you take the limit as x goes to minus infinite plus infinite. So we don't have maximum, global maxima. However, because this is sort of the unique point where it reached the local mean, and so we can say that it's not only local minima, it's in fact the global. So x equal to 1 is in fact also global minima, right? So at x equal to 1, what is the global minima? To find the value at the global minima, you have to substitute x equal to 1, right? This becomes into the function, so it becomes 1 minus 4, so this is minus 3. So both local and global minima of the function is minus 3, and it occurs at x equal to 1. One more example. Now we have x squared minus 3 multiplied by e to the x. Again, the graph is shown on the right. Again, we would like to identify the intervals where the function is decreasing, and we want to investigate extrema. So again, we start with taking the derivative. So what is derivative? Well, this is the product rule. So derivative of x squared minus 3 is 2 times x, e to the x, and plus x squared minus 3 times derivative of x, e to the x is e to the x. So we have x squared plus 2x minus 3 times e to the x. Okay, if you know the quadratic formula, you can solve the, so I need to set it equal to 0, so you can solve this quadratic equation, or you can simply maybe factorize. you can do x plus 3x minus 1 times e to the x equal to 0. So e to the x is never 0, right? So the only way this can be 0 is if x is minus 3 or if x is 1. So these are my critical points, right? Again, so I plot these values on my real line. And again, I pick any value that's less than minus 3 or just assume it. If x is less than minus 3, then I see that the first one is negative, the second one is also negative, so this becomes positive, right? So here it's increasing. Between minus 3 and 1, let's say, for example, x equal to 0, then this is positive, this is negative, so this is negative. From 1 to onwards, for example, you can plug in x equal to 2, then this is positive, this is also positive, so this is going to be positive. So what I see is my function here is sort of increasing, then I have a decreasing, then I have increasing, right? Increasing. So this is sort of slightly different, right? But we kind of see, right? So here I have so increasing function, and then starting from some point it started decreasing until I get 1, and then it started increasing again, right? But again, from the first derivative, when I move from 1 to from 1, right? If I passed 1 from left to right, my function is the derivative changing from minus to plus, right? So it's decreasing. So this point is, so x equal to 1 is at x. I have local minima, and what is this minimum point? You just substitute f of 1, right? So this is going to be into the equation. So this is minus 2 times e to the 1, whatever it is. And how about x to the x minus 3, right? X minus 3 is the sign is changing from plus to minus, right? So it sort of increases and then decreases. So this is the peak, right? So this is local maxima. And what is the value? You plug in minus 3, you get 9 square, sorry, minus 3 square is 9, minus 3, so this is 6 e to the x. So here we have local maxima, local, and here we get local minima. Now, I mean, from the picture we see that this local minima in fact is global, right? But how do we know it? Maybe this function sort of will decrease and then maybe become even smaller, right? So how do we do it? Well, you have to take the limit, right? So you have to go ahead and take a limit as x goes to minus infinite of this function x squared minus 3 e to the x. So well, so what happens? What happens? So we see that this is positive, right? This is sort of positive, but this is sort of decreasing to 0, right? And this is exponential function. So this is start decreasing, but it never becomes less than, right? It never becomes less than 0, right? Because all of these values are positive, right? So this is always sort of positive, but it's sort of the limit is sort of approaching 0. Well, we don't see it yet, right? So we could apply some other methods, but we don't want to do it at this point. So this is kind of so it's definitely bigger than this minus 2, right? So minus 2 to the e. So it means in fact here I not only have a local minima, in fact I have a global minima again. Now another question is, how about this point? This is my local maxima. Can this be a global? Well, you can also look at the behavior, end behavior, right? When x is going plus infinite, x squared minus 3 e to the x. Well, in this case, this is like infinite times infinite. So this is infinite, right? So here it's going to infinite. So because this is infinite, it means there is no global maxima. Okay, so this is how you should investigate monotonicity, and this is how you apply the first derivative test. Later we're going to see the second derivative test.